So this video is the first of two devoted to the study of compact self-adjoint operators in Hilbert spaces. So let us recall the definition of a self-adjoint operator on an Hilbert space. It's a continuous operator such that it's equal to its adjoint, which means that for any x and y in H, Ax scalar H equal to x scalar H. Okay. And let us see an example. We already met this operator. We have an infinite matrix such that the square is a convergent series as the series indexed by on N2. And we have this symmetry hypothesis that this matrix, infinite matrix, is in some sense Hermitian or symmetric in the real case, and we define this. We already saw that this is compact, and this is an easy exercise to see it's self-adjoint, that's like really like matrices. And compact means, I recall, that the range, you take the range of the unit ball, you take the closure, and this is compact. Okay. So the first theorem, first proposition, in fact it's not very complicated, is to prove that a self-adjoint operator satisfies the following. You can compute the norm of A simply by taking the supremum for u equal to 1 of AUU. Of course, we know that the norm of L of H, this is the supremum of the real part of AU, V, when U and V are of norm 1. And if we define the supremum here when U equals to V, so we take the supremum in a smaller set, so we have this inequality, of course. Then we have to prove the opposite inequality. So here, when you compute here, the quadratic terms, UU and VV disappear, and you have only AUV, or some permutation of this, but because of self-adjointness, this is equal to the real part of AUV. And this here, by definition of N, and through an homogeneity argument, we have that this is less than m over 4, this quantity. And now we use the parallelogram inequality, and we see that if this is 1, the fact that we have this relation, this is on Hilbert space, of course this is 1, and 2 times 2 is 4, this is 4, and this is less than m, and we are done. Now, what we are going to prove is something very important, is that when we have a compact self-adjoint operator on a separable Hilbert space, then there is a unit vector on the sphere of H such that we have, in fact, M0, this supremum is in fact a maximum. In other terms, it's reached. And it's reached in a vector which is an eigenvector of A for the eigenvalue plus or minus M0. The previous proposition claims exactly that if M0 equal to 0, then A equal to 0. So there is nothing to prove, so we can assume that M0 is positive. And then changing A into minus A, we can assume that there is no absolute value here, but M0, this is the supremum of AXX. Okay. Now we are going to consider a maximizing sequence, in other terms, a sequence such that the limit when n tends to infinity of an scalar xn equal to m0. Okay. Now, compactness, weak compactness of the unit ball, and the fact that A is compact, that weak compactness of the unit ball gives this, and the compactness of A allows to say that there is a y such that we have this. Of course, here there is an extraction we don't note anymore. Okay. Now we have to prove that with all this, we have this. Okay. Weak convergence gives this. This weak convergence, it gives this. But the self-adjointness of A says this is this. And the self-adjointness of A says also this is the limit here, and this is AXN Z. But because we have convergence, this is YZ. And this is true for any Z, so this is equal. So we have the result. Now, let us observe that we have this. Why do we have this? We have this because xan dot n tends to axx. Why? Because here we have strong convergence and here we have weak convergence. So we have convergence. But, of course, we have this. And this implies that the norm of x is greater than 1. But x is the weak limit of a sequence xn of norm 1. So the norm of x is less or equal to 1. So it's equal to 1. And we have exactly that this is equal to m0. Okay. So the first part of the proposition is proved. Now we are going to prove the eigenvalue property, which is in fact an easy exercise of linear algebra. So A is a self-adjoint operator, x0 a vector of the unit sphere, such that ax0 scalar x0 equals to plus or minus m0. Then x0 is an eigenvector of A associated with the eigenvalue plus or minus m0. Okay, so we can assume that ax0 scalar x0 equal to m0. And now by homogeneity, we have that ax x is less than m0 x squared. So what we have for any h and lambda, this is positive. When we develop the fact that m0 x0 equal m0 equal a x0 x0, we infer that the result of this is this. And here we can simplify. And here what we have is that the real part of this is positive for any h. But changing h into minus h implies we have mx0, ax0, real part of this equal to 0. And then apply this with IH, that we have m0, and not only for real part, but for all this. This means exactly that ax0 equal to m0 x0. And we are done. In the next video, we are going to prove the structure theorem for self-adjoint compact operators.